everyone, welcome back to Alkaline Hydroxide 784. I know the video is very late. Please bear with me. I'm quite like it's not really just being busy or anything, but I'm just like really tired, so yeah. Okay, but right now I'm not that tired, so I'm gonna record this. And actually, I did record this once, but I realized that I was so sleep deprived that I don't even remember what I was saying. So I feel like I might not have done a very good job because I remember zoning out at least 4 times when I was recording that. So I'm just gonna redo it in a more clear, alert state so that at least you can understand what I'm saying. Right, so by the way, there is sleep. There's a video on sleep deprivation. So, because I was so sleep deprived, I decided to record what it feels like to be sleep deprived. Yes, sounds perfect. If you want, you can go watch it. Let's get back to the physics series right now. So we are doing nuclear physics today, and yeah, we'll get right into it. So the first learning outcome is about the Rutherford uh, alpha particle scattering experiment, and yeah, let's just go into that. So you know what's an alpha particle, right? It is a helium nuclei. Yeah, it's just a helium nuclei. It's without the electrons. So the helium nuclei has two neutrons and two protons. And since it's a nuclei and not the entire atom is positively charged. Yeah. So what happens in this experiment is that you put this gold foil and behind there's a thing to capture any particles, like this curved capturing thing, like a screen, and then you pass a bunch of alpha particles through the gold foil and see what happens to them, whether they actually pass through, whether they are reflected or deflected or whatever happens. So if let's say the particle doesn't pass through, that means the gold foil is blocking it. But the first result that was found in the experiment was that most of the particles went through the gold foil straight ahead, like they went and hit right straight in the middle of the screen. So that means there is quite a lot of gap between each of the gold atoms, and therefore the helium nuclei can easily pass through the gaps there. And the other big thing that they found was that the nuclei that actually interacted with atoms, which would be a very small number of them, deflected almost 180 degrees to the sides of the curved screen, which means that when they do interact, the nuclei is the nuclei is actually repelling this particular nuclei, so they are both positively charged and they have quite a good charge density down there. So the idea is that this proves that the atomic nucleus actually exists and is positively charged, just like the helium nuclei. And it's also really small because otherwise the helium nuclei wouldn't have easily passed through the gold foil. But since it's so small, most of the foil is literally just space, and the nuclei can easily pass through this space. If there's any background noise, I apologize for that. But at least I'm talking properly right now, so that's better than me talking in a sleep deprived state. Okay, so the next learning outcome is distinguishing between nucleon number and proton number. I think we already know what these things mean. Like the nucleon number is the number of both protons and neutrons, which is also the mass number. And proton number is the atomic number, which is what defines the actual element. So if you look at the next learning outcome, it's about isotopic forms, which means that the same element, it will always have the same number of protons. So let's say you have carbon, it always has 6 protons no matter what carbon it is. But there's various kinds of carbon like carbon 12, carbon 13, carbon 14, and they're all isotopes because their nucleon numbers are different. So they each have different numbers of neutrons, which changes their nucleon number as well. But if let's say you change the proton number in carbon from 6 to 7, it's no longer carbon, it becomes nitrogen. Right? So so technically you should like if you change the number of protons, it becomes a different element. But if you change the number of neutrons, it's still the same element but an isotope of the element. Yeah. So the next one is about the notation. So I will write it down here, how you represent nuclides. So nuclides are basically the atom with the representation of the, nucleon number and proton number. So it can represent any particular atom and anything that you can see. So yeah, so when you write the nuclide, you would be writing the element symbol first. Like for example, in this equation that they've given here, for 14,7 nitrogen plus 4,2 helium becomes 17,8 oxygen plus 1,1 hydrogen. So for example, if you look at the nitrogen, you write the nitrogen first, in a capital letter, N, I suppose, and then you put your 14 on the top, which is the nucleon number, and the 7 below, which is the proton number. And these two numbers are to the left of the nitrogen signs, so or that N, to the left of the N. That's how you write these equations. And you have to make sure that all of these numbers are somewhat balanced, so which is what we see the next learning outcome. The nucleon number, charge and mass energy are all conserved in nuclear processes. So the nucleon number, if you look at the equation that they've given in the syllabus, we can see that 14, 4, 17, 1. So they both add up to 18. So the nucleon number is the same. The charge would be conserved as well. So basically the number, like the neutrons, protons and electrons are all like somewhat conserved in a way. It's just that they're either with or separated from the atom, or they could be converted to energy sometimes, but in a way generally the nucleon number and charge are all conserved. So the mass energy is also conserved, and the fact that it says mass energy and not just mass means a big thing, because we are looking at nuclear physics here, not just normal chemistry. So yeah, I will explain more of that soon. Yeah, or like now as I'll explain it bit by bit as I continue down. Yes. So the next learning outcome is about the concept of mass defect. I kept saying deficit the other time, the first time that I recorded it, and I have no idea why. But it's mass defect. Yes. So the concept of mass defect is when it seems like suddenly the mass has been lost. So when you combine two atoms together, then suddenly the mass decreases by a very teeny bit. But of course you may not really notice it's a bit hard to measure, but technically it decreases. And this is known as mass defect. And why does this happen? This is because the mass is actually converted into energy. There's a reason why we say the conversion of mass energy and not just mass. So the mass energy is like one and the same thing kind of a thing. So the mass defect is converted into energy which is released. Yeah. So that's what happens when you combine two things together. Yay. Right, so the next one is recall and apply the equivalence relationship, which we have just established that there's a equivalence between mass and energy. And the one and only equation that we all remember very well is E equals to mc square. Yes, this is where it comes into play. You always heard this equation many times, and you wondered where exactly you can use it. This is the topic to use it in. So to explain this equation in greater detail, the E is of course energy and m is of course mass. The c squared is the speed of light squared, and of course the speed of light is, let's say together, 3 times 10 to the power of 8. Yes, I remember that like the back of my hand. Yes. So this equation basically says that energy is proportional to the mass defect, and the proportionality constant is the square of the speed of light, which would be equal to like what, 9 times 10 to the power 16. That's a huge number. Yes, that's why the mass defect is super small. You can hardly notice it, but because of the 10 to the power 16, the energy is actually noticeable. Yes, right. So you can use your calculator, type everything in, and you are good to go. So just use that to solve your questions. So like the idea is it'll give you an equation and then you see maybe it'll give you the actual atomic mass of each of the nuclides, and what you do is you see the product versus the reactants, see what's the mass defect from that is created by the reaction, and use that mass defect as your m, and E equals to mc squared. Yeah, so make sure your m is in the right units. Don't put it in as something 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 AMU. Convert it to SI units so that you can actually times it by the speed of light to get energy. Yes, speed of light squared, I mean, yeah. So that's how you do these questions. Shouldn't be too hard. Okay, so how does this work? Like what exactly is this energy that comes? So we look at the concept of nuclear binding energy and its relation to mass defect. So this energy is actually nuclear binding energy, and basically the idea is when you're combining two of the or like separating two things together, you know, there's like this particular energy within the nucleus itself, because otherwise the neutrons and protons wouldn't just stay together just like that. They need something to actually keep them together, and this is what you consider as the nuclear binding energy in a way. But the way that you define it is the energy required to separate all of the nucleons in the nucleus. Yeah, that is the definition of nuclear binding energy. And the average would be the nuclear binding energy over the number of nucleons. So that is the definition of this particular energy. And this is where we find out how to get mass defect from energy instead. So you see the difference in like the energy gain or loss based on whether the nuclei are combining or separating or whatever. And once you get the difference, you can use it to calculate your mass defect or whatever, using a famous little equation over there. Yes. So basically, what is the difference? Like, so how does the binding energy vary over all of the elements? Because you may be thinking, okay, it seems like something that's common with all the like neutrons and proton. Protons. Yes, I almost said photon. Oh my. Yes. So, but the energy is slightly different as you increase the number of nucleons in your element. I mean in your atom or nuclei, whatever you want to say. So, because the more protons you put in, the higher, um, you know, resistance you get when it comes to putting them together, because they're all positively charged. Because neutrons are okay, they're like neutral, but protons are positively charged. So the more protons you have, the more energy that that seems to be kept within that nucleon. So the nuclear binding energy increases from the first few elements. It increases to a maximum around 60, around iron. Iron is like usually the highest one, iron and zinc. And from there it decreases a little bit more gradually, and the more it decreases, the more likely you get the radioactive nuclei, because they can't keep themselves together and they need to separate. Yeah. So what happens in this is that if you're looking at the that's the graph lah. I'll just show you the graph first. Of course, the next one is the relevance of this to nuclear fusion and fission, and I'll be explaining that right now. So if you're looking at the left side of the graph, it's all the smaller elements, and you can actually fuse them together to get a bigger element, because then the binding energy will increase. So you imagine that you want to get to a higher binding energy, so it takes more energy to actually pull it apart. So in other words, it's more stable. It's a more stable nuclei. So when you combine smaller nuclei, you get towards the iron peak there. And of course, on the other side also, you would want to make your nuclei smaller so that you can get to a more stable nuclei. So that's the general idea in the sense. So the fusion is for the smaller ones combining together, and fission is for stuff like uranium to become smaller, like to split up and to two smaller nuclei which each have a higher binding energy than uranium itself. Yeah, so I mean higher average binding energy. Yes. So that's the reason why the graph is binding energy per nucleon, or the average binding energy, as I would probably want to say it, but it's per nucleons. Because if you took the overall binding energy, obviously the more nucleons you have, the more likely you're gonna have a higher binding energy. But the one that has the true, best binding energy is the iron and zinc area. So that's why you still see all this fusion and fission going on. Okay, so the next one, show an understanding of the spontaneous and random nature of nuclear decay. So nuclear decay is something that just happens. That's literally what it means. It literally just happens. It's spontaneous, it's random, you can never know when exactly it will happen. But it happens. You just know that it happens, but you don't know when. And why does this happen? Well, I just mentioned the higher the bigger elements tend to be a bit unstable, like uranium, polonium, plutonium, I don't know, all the radioactive stuff. So they tend to want to break down. They break down into smaller nuclei and become more stable. But we don't know when they will do it. They still have a decent amount of binding energy. It's just that they just require a certain period of time where they suddenly have enough energy to split up or something. So once that happens, you can get to this whole idea of you know nuclear decay. And this will be quite spontaneous, it'll be quite random. You don't need any external input, it just does it on its own at some certain fluctuation of energy at a certain point of time. Yeah, so but you might be wondering, how come you know that it is random? What if it's actually really orderly and we just didn't notice it? Well, we did notice that it's random because if you look at the Geiger counter, you put it next to the uranium, the count rate may not be very stable. It will keep increasing and decreasing. It will be around a range, but it will keep increasing and decreasing, which means that the decay is quite random. And for some of them, the fluctuations even worse. So it won't even have like a proper range. It'll just be like any random number, and that's like pretty much the idea of the randomness of this. So yeah, might be wondering how to quantify this, but we'll be looking at that later on. I'll show you how to quantify all of this stuff, like how do you quantify the count of the particles, the radioactive particles that are emitted by these things, and how you represent that in equations later on. But before that, we will talk about the other things that you need to know when you're using a Geiger counter or measuring stuff like that. First of all, you need to know that even if you don't have uranium there, you're gonna be getting some count rate on the Geiger counter. And you might be wondering, hey, is it spoiled or something? No, it's not spoiled. It's actually the background radiation. It's not, even though most of the elements tend to be in their non-radioactive form, there's still definitely some radioactive atoms here and there, and they'll definitely be doing something. They'll be decaying or emitting some kind of radiation, and this will contribute to your background noise. And yeah, you need to take note of this when you're measuring the count rate of something. I mean, or the question mentioned someone measuring something. You need to take note if there's what's the background radiation number and versus the count rate of the actual radioactive thing. So that's why it's quite important because if you don't take note of it, you're kind of likely to over report the number of counts, and it may actually cause problems. Because if you think about it, like if you have um your decay will decrease exponentially. So when you have that same base number there the entire time, it may actually cause some trouble if you don't remove it. Yeah. So the next one is showing an understanding of the nature of alpha, beta, and gamma radiation. So alpha, beta, and gamma. Of course, the thing is, right, different Geiger counters can measure more of a certain radiation, as I saw in a video just recently. So just that's good to know. But you don't really need to know that for your A levels. Just know that Geiger counters can count radiation. Yeah, like the number of particles that are emitted. So what is alpha radiation? We learned at the very beginning, which is the fact that alpha particles are helium nuclei. So they have two protons and two neutrons, and they have a charge of 2 plus. Yeah. So that's alpha particles. Beta particles um, are basically protons, or if you want to look at it in a different way, hydrogen nuclei. So hydrogen nuclei are basically proton. It's just one single proton. Because a hydrogen only has one proton and one electron, and once you remove the electron, it's literally just a proton. Yeah. Wow. Yes. And gamma radiations are not actual matter, but it is light. So gamma waves are a form of light, or EMR if you want to call it that way, electromagnetic radiation, and therefore they have a wavelength and they have actual energy like light does. Yeah. So that is what gamma radiations are. So how do each of these come about? Yes. So alpha radiation generally comes about when you have this big atom and it wants to decay, but sometimes it doesn't split up into two equally sized nuclei, but instead just emits an alpha particle. So for example, yeah, I need to think of an example. So let's say you have your, okay, I'm gonna scroll to I'm gonna get a periodic table out. And yeah, so the idea is that a big nuclei will emit these two proton, two neutron thing just to make their life easier, kind of. And it allows them to become a more stable element. Yes. So let's look at something that is radioactive. Let me see. Okay, let's look at uranium. Yes, we always look at uranium. So basically all the isotopes of uranium are actually unstable. So even if you use uranium 92, you can still have alpha decay. So uranium 92, if it were to decay, what would it become? You would remove 4 nucleons out of it. So that means so this 92 is actually the proton number. So the mass number that you see here is 238. So you'll say this is uranium 238 maybe. So you remove 2 neutrons and 2 protons, then your uranium will then become 23690, which then is not uranium, it's no longer uranium but instead thorium. Yeah, so it is 236 thorium instead of 238 uranium. Yeah, that's what happens when you remove the alpha nucleus from it. And the next one is beta radius, radiation, beta radius. Okay, so beta radiation is when you emit a hydrogen or proton. Sorry, not exactly hydrogen, but proton. So this happens when basically how this works is the element actually becomes the so-called larger element. So the nucleon number doesn't change, but instead one of the neutrons becomes a proton. That's basically, not one of the neutrons become an electron, I mean, kind of. Yeah. Oh wait, beta radiation isn't a proton, it's an electron or a positron. I'm so sorry. Sorry for that mistake. But beta radiation is actually electrons. It's not protons, sorry. But the proton is what is the result of the beta radiation. So basically what happens is a neutron becomes a proton by losing an electron. Yeah, that's what happens in the element. So let's say if uranium were to undergo beta radiation, it will become neptunium. It won't become thorium, but it will become neptunium because it increases its proton number. But the nucleon number is the same. So yeah. But it's very unlikely that uranium will become neptunium because neptunium is probably even more unstable than uranium is. So I don't know. Yeah. Yeah, here's the equation anyway, so. And then gamma radiation, of course, is a high energy wave. So here we don't have any change in the element or whatever, but more like the element just happens to be super excited and very unstable. So the excess energy in there then becomes a light wave, which is the gamma wave, and that kind of travels really far and also quite hard to block because it's light, it's not a particle. Yeah. So if you look at alpha, beta, and gamma, the smaller the thing is, because gamma is a photon, and I don't even know if it has a space, like how much space it even takes up. So you look at it and you see that, okay, so alpha particles are the largest and they're easily blocked by a piece of paper. Of course, we found out earlier that somehow they can pass through gold foil, but the thing is you can generally stop them with a piece of paper, so yeah. And beta particles, sure, electrons um, can pass through more things. They can go through paper. They can go through one piece of paper maybe, but they can but they can actually go through to your skin and stuff like that, but they can be blocked with thicker pieces of paper or plastic or something like that. And gamma radiation cannot be stopped that easily, and you need something like lead in order to stop it because it's light. It can literally just go through your paper like it's nothing. Yeah. So, and it comes to your skin per se, alpha doesn't easily, it's very hard for alpha radiation to penetrate your skin, but if it's inside you, it can cause some damage. If it's a beta radiation, it may pass through your skin a bit, but it's not really the worst radiation you might be thinking of. But gamma radiation can definitely pass through you, so you better be careful about that, huh? So, yeah, that's pretty much it. And of course, there's other kinds of radiation like X-rays and actual neutrons and stuff like that, but you don't need to worry about that. In fact, you already learned about X-rays, so I don't think I need to. But the what was that word? I don't know. I don't need to like say it again. Yeah. Alright. So the next one is the conservation laws for energy and momentum in beta decay. Oh yeah, so actually before we move on, there's a bracket about knowledge of positron emission is not required. And that's because beta radiation can include positrons as well. And if you didn't know what a positron is, it is actually an anti-particle version of the electron. So yeah, it's an anti-electron. So it has a positive charge, but it has the same mass as the electron, and the magnitude of the charge is the same as that of the electron. Yeah, that's a positron. And sometimes a positron can be emitted by in terms of beta radiation, but usually for your paper you don't need to worry about this. Just write electron can. Don't need to worry about positrons. Okay, so the next learning objective is the conservation laws and beta decay. So in beta decay, we see that the electron is, you know, emitted, and even though the electron is emitted and the neutron becomes a a proton, and the mass is somewhat conserved in a way, but we there's this issue with the momentum thing. It seems like as if the momentum isn't conserved when you look at it at first glance, because the like when you write the equation and then you get the actual data, the momentum doesn't seem to be conserved. But you need the momentum to be conserved. So what happens is that there is actually another small particle. It's like a very small amount of momentum difference or energy difference. And this small particle, there's this some other particle that somehow occurs in this whole reaction. And that's what they call the neutrino. It's represented with a weird tilted V thing. Yeah, but actually usually it's a anti-neutrino, but you don't need to worry about it being an anti-neutrino. You can just write neutrino. The anti-neutrino is represented with a dash on top of the V, kind of. Yeah, so the neutrino is what makes up for the rest of the momentum conservation or energy conservation, and this allows you to see that okay, so the nucleus plus whatever is hitting it, maybe alpha particle or something, ends up becoming something like the momentum is such that the of the nucleus just explodes on its own. Like the the pathway of each of them is such that you can actually see, oh, there's another third particle going the other way. So it'll look like a Y, like they're going in the three different directions basically. Yeah, so there's a neutrino. A. So the next learning outcome is the activity and decay constant and the equation related to that. So activity of the sample is the kind of like the number, like the count rate of stuff that you get, like the overall count rate, and the decay constant is the average count rate per time, and per number of particles. So the idea is that activity is equals the decay constant times the number of particles in the sample. And the greater the number of particles, the more activity you get. So activity is the overall count rate per minute or per second or whatever time base you want. Yes, that's the general idea. Okay, so radioactive decay is also exponential. So as you can see from this equation, if let's say you wanted to approach this in a mathematical way, as we do here in engineering, we can convert this to dA or dt equals to you know, d lambda n over t. Yes. So, and lambda is constant because it's literally called a constant. So that will then be equals to lambda dn over t. So how does n change per se? Yeah. I don't know what I just did. Sorry. So dn over t okay, actually this doesn't work, never mind. We need like a certain equation for it to work. You can't just anyhow do it. Okay, sorry. So let's just go to the actual equation. And it's kind of exponential, so it's like dn or dt is proportional to n itself. That's what I wanted to say, something like that. So that will give you a exponential relationship. Okay. So the equation that they've given here in the syllabus is x equals to x naught exponent e to the power of negative lambda t, right? Yeah. So x can be literally anything. It can be activity, it can be number, yeah, the n, or it can be the count rate itself, because the count rate is somewhat proportional to the number of particles that is emitted in a way. Yeah. So let's say if you use activity, so the activity is the initial activity times e to the power of negative lambda t. So why is there this negative lambda t? It is because of course lambda is the decay constant, and we know that it's like per time kind of, yeah, and the t is the time, so it then becomes the average number in a way. And yeah, so from this particular relationship you can then infer that the decay constant is equals to ln 2 over t half, which is where t half is the half-life, and half-life is the amount of time it takes for the number of particles to become half of the original number. So in this scenario, if you think about it, if you have t half, the lambda t will then become something that makes e into half. So how do you get half out of the e? You will then put negative ln 2 or ln half instead. So e to the power of ln half is then equals to half. And that is and since there's a negative sign, the negative sign in the original equation, that means that we have to convert the ln half into a negative ln 2. And therefore, if you look at it this way, the ln 2 is then equals to the lambda t, and in this scenario t is t half, so half-life, and therefore lambda is equals to ln 2 over t half, and vice versa. Yeah, so it's kind of like your chemistry kinetics, your rate constant, the same logic for your first order reaction. Yeah, it's the same thing. So now now you can look at the effects of direct and indirect effects of ionizing radiation, and that will be the last learning outcome for today. So ionizing radiation is what it means. It has enough energy to detach electrons from atoms or molecules and then ionize them. So ion, anion, cation. So you remove the electron, it becomes an ion. So what happens is like if you look at light itself, the normal light that you see every day is non-ionizing. So your phone, the stuff your phone emits is not ionizing. It is quite, the wavelength is quite long, so it won't really ionize anything. But gamma rays, X-rays, ultraviolet, they are somewhat ionizing. The higher frequency ultraviolet. But if it's more of the light spectrum, the visible spectrum or higher up is not, like higher, longer wavelength is not very ionizing. Yeah. So what does ionizing radiation do? If you were to burn, you can get burns on your skin, let's say, or burns between yourself as well, possible. And if it's like indirect, you can get radiation poisoning or things like that, so, or cancer, or stuff that happens to you because the radiation can mess up your biochemistry. If you think about it, your cells are made up of a lot of chemical molecules, and if you have something making ions out of them, it's not going to end well if you think about it. Yeah, so of course your body has a way to deal with this. So we have stuff like the like how we have antioxidants, we have stuff to deal with ionizing radiation. But of course, if you have too much of it at too little of a time, you will you might die. But if it's a long period of time but not enough to kill you, you'll then be killed after a long time. Yeah, that's pretty much it. So that's why you shouldn't expose yourself to ionizing radiation, and you should be careful about it. Yeah. So we are kind of done, which I hope I make more sense this time around. Of course, you can't really hear the first time that I recorded it because there's no reason for me to upload that. But if you do want me to upload it, I don't really want to make a video for it. It's just audio. Yeah. Okay. So, yeah, that's about it. I think we are done. This is the last chapter in the H2 physics syllabus, and that's why all the more I didn't want to mess it up, and that's why I re-recorded it. But this will not be the end of the series. I think we still have one more episode for the practical, one or two more. I don't know how much time I need to actually explain the practical, and of course one more episode for the um, exam itself, and what are the things that you need to take note for your physics exam in general. Okay, so I think we're done. I hope you found this video useful. I know it's long, but hopefully you can have a better understanding of nuclear physics now, and you can do your nuclear physics questions well. I think it's quite a fun topic too. Yeah. So yeah, now if you have any comments or feedback on what you want to see in the future, because this series will come to an end eventually by the end of next month at least. So, you what the next series you want to see, you can comment below. Or if you don't want to see a new series and you just want me to continue with the chemistry series itself and then just finish that first, you can say that as well. Um, yeah, we'll see if there's any other special episode you want me to do, like maybe some adulting related stuff or anything. Please do comment below. And with that, I would like to say thank you and bye.